We're going to get immediately into chapter 13, and we're going to start talking about solutions. Okay, so again, for this chapter, you actually need to review quite a bit from your Chem 110. In particular, you want to, again, learn how to draw your most probable Lewis dot structures. Again, you're going to use the octet rule to get to a good structure very quickly, but then you have to use formal charges to make sure that you have the most probable structure. And the reason we're going to do that is we need to understand the bonds, what atoms are bound to what, and the molecular polarity of the molecule. So bonds, individual bonds can be polar and have dipole moments, but the overall molecule may not be polar, right? So symmetry kills polarity. So if you have a symmetric molecule, the dipole moments are going to cancel and you're going to have a nonpolar molecule. So again, you need to go back and review molecular polarity. We're also going to start talking about solutions. So we're going to talk about different concentrations. We've already learned about molarity, or the molar concentration of solution. So how many moles of something dissolved in the solvent, right? And we also talked about diluting equations and the dilution equation, M1V1 equals M2V2. So you need to go back and review that. And one of the most important things are intermolecular forces from chapter 9. Now, I will briefly, very briefly review these things, but not enough for you to get a full command of it. So you're going to need to go back and review that stuff, okay? Okay, so solutions are just homogeneous mixtures. Okay, so what that means is that when you dissolve something in your solvent, those particles dissociate from the solid and then float around in solution. And they do that evenly. So if I took a small sample, 1 milliliter sample from one part of the solution and took a 1 milliliter sample from another part of the solution, and I was somehow able to count how many particles in each, they would basically be the same, okay? And these particles are not going to settle out of solution. And the solution itself is either going to be clear or it's going to be colored, but you'll be able to see through it. It'll be transparent. And that's because the particles are very small. We're talking like atoms at 0.1 nanometers to relatively small molecules up to about 2 nanometers, okay? Now, we could have other solutions too, which are called colloids. Now, colloids are homogeneous solutions, okay, but they, okay, that's just irritating me. I'm moving my camera. Okay, so, whoa. Okay. Okay, so colloids are also homogeneous solutions, but this time the particles are large. Okay, they're anywhere from 2 to 500 nanometers, and they're so big that they make the solution opaque. But they're still small enough that the thermal forces, the thermal energy within the solution is enough to keep them moving around and they don't settle out, right? They don't fall to the bottom of their container. Example of this is milk, right? Milk is a colloidal suspension and it should not be settling out. If it's starting to settle out, your milk is spoiled, okay? Because it's forming now particles that are even greater than 500 nanometers. Okay, so that's what a colloidal solution is. And then we have what are called suspensions. Suspensions have really big particles. They're greater than 500 nanometers. Now, their mass is so great that the gravitational forces are greater than the thermal motion forces within the solution. And these particles begin to fall out of solution, or they form a solid at the bottom of your liquid, right? So they separate out. So these are not homogeneous. An example of this would be paint. So paint actually has two parts. It has a colloidal part and then it has a suspension part. So there's particles in paint, okay, usually titanium dioxide. And these particles are big, so they actually separate out. They fall down. So that's why you always have to mix up your paint. So paint is a suspension. It contains particles that are so large that gravity can actually pull them out of solution. Okay, so those are the different types of solutions. We are going to not talk about colloids or suspensions at all. We are going to focus on solutions. Again, solutions are homogeneous mixtures. Okay. Now, a solution is simply composed of two or more substances. It could be the ocean, for example, is basically a saltwater solution. It contains literally thousands of different types of ions, and it is a homogeneous solution, okay? And it can consist of ions or molecules. So if you took a glass of water and you put in some sugar and stirred it in, that sugar is soluble. It's going to dissolve in the water. It's going to form a homogeneous solution where the sugar molecules spread throughout. And then if you took that glass of sugar water and you took your table salt, which is just sodium chloride, and you put that in the same glass of water, mix it up, well, sodium chloride is a strong electrolyte. It's going to completely dissociate and form sodium and chloride ions. And it too is going to form a homogeneous mixture. So in that case, you would have a homogeneous mixture of neutral sugar molecules, sodium ions, and chloride ions. Okay, so there would be three components. What we're going to call three solutes. Now, solutions can exist as either gases, liquids, or solids. Okay, an alternate definition basically is a homogeneous mixture composed of a solute and a solvent. The solvent is simply the greater amount of the two, okay? So the solvent is just the greater amount of the two, the solute being the lesser amount. The solvent, again, is the dissolving medium. It's, again, the more abundant component. And the solute is just that which we dissolved into our solvent. And again, it's got to form a homogeneous mixture, okay, to form a true solution. Now, liquid solutions are obtained simply through the dissolution of a solid, liquid, or a gas into the medium. Okay, so solid. So for example, if we took sodium chloride and we dissolved that solid sodium chloride in water, that salt in water, it's going to dissolve and form a homogeneous mixture. If we take pure ethanol, okay, also known as pure grain, right? If we take that pure ethanol and we mix it with water, it's going to completely dissolve into the water, mix at 100%, and form a homogeneous mixture. We could also take a gas, for example, carbon dioxide. So if we take water and we seal off the water with a lid and then pump carbon dioxide into it, some of that carbon dioxide is going to dissolve into the water. And some of that dissolved carbon dioxide, not all of it, but some of that dissolved carbon dioxide is actually going to go back to carbonic acid, okay? And we're going to talk about that kind of stuff as the course progresses. Okay, so many inorganic compounds are soluble in water and they completely dissociate. Again, we call that our strong electrolytes. So it's going to be imperative that you are able to recognize a strong electrolyte from a weak electrolyte. And we spent a lot, again, we spent a lot of that. And again, watching TV isn't going to help you learn this course. But a strong electrolyte, again, you need to recognize your strong electrolyte as opposed to weak or non-electrolytes. I don't really expect you to know the difference between weak and non-electrolytes. That can be difficult. But strong electrolytes, on the other hand, you've got to be able to recognize a strong electrolyte from a non-strong electrolyte, okay? Now, other inorganic compounds we call insoluble. So for salts and hydroxide bases, we use our solubility rules for that, right? If they're soluble, aqueous, and again, this only applies to salts and the hydroxides. If they're soluble, they're strong electrolytes. If they're insoluble, they only partially dissociate, and we consider them to be weak electrolytes, okay? And then some molecular compounds are also soluble. Again, sugar, a prime example, right? I dissolve sugar in water, which is a molecular compound. But in this case, most molecular compounds are non-electrolytes. So sugar is soluble, it's aqueous, but it doesn't dissociate at all. It's not even a weak electrolyte. It doesn't dissociate at all, okay? Now, there are some exceptions to that, and those are the carboxylic acids. Those are neutral molecular compounds, but those carboxylic acids do partially dissociate in water. So we would consider those molecular compounds as being weak electrolytes. So that's the only exception again. And we're also going to find out that the neutral nitrogen-containing molecules are also going to be an exception. So we're going to find out that the neutral nitrogen molecules always dissolve in water, because we're going to find out they have similar intermolecular forces, and that's what allows things to dissolve. Like dissolves like. We're going to learn that. And that means that things with like intermolecular forces will dissolve in other things with a similar intermolecular forces. And so we're going to find out that nitrogen-containing molecules, as long as the nitrogen has a lone pair, is very similar to the intermolecular forces of water, and therefore they all dissolve in water. So they're all aqueous, just like I made you memorize, for those of you who had me, I made you memorize ammonia, NH3, as being a soluble compound and a weak base. Now, the reason I made you memorize that is because now you can apply that to all neutral nitrogen-containing molecules in which the nitrogen has a lone pair. They're all going to be soluble, and they're all going to act as weak bases, okay? Okay, next let's talk about miscible and immiscible. So in this case, I'm showing you an example of immiscible fluids. I have water and let's say gasoline. So these are big, long hydrocarbons. And we're going to find out that water has very different intermolecular forces than gasoline does, and therefore they don't mix. Now, a few water molecules will get into the gasoline, and a few gasoline molecules will get into the water, but very, very, very little, okay? And we can see that here. In this case, the water's on the bottom, the gasoline, this isn't gasoline, whatever this substance is, has a higher density than the water. So the water's on top, and this substance with a higher density is on the bottom, okay? So again, they don't mix because all this has is basically London forces, is where the molecules display London forces, dipole-dipole interactions, and hydrogen bonding. So the water displays all three types of intermolecular forces, with the hydrogen bonding being the strongest. And therefore, there's no reason for the water molecules to leave go of one another and go into the hydrocarbon, or vice versa, open up to allow the hydrocarbon to come in. There's strong attractive forces between each other. So therefore, they don't mix, and we call these immiscible fluids. On the other hand, some materials are miscible. So for example, this is acetic acid, and this is water. Well, the acetic acid, even though most of it is undissociated, less than 1% of this acid dissociates into the H+, okay, which you can't see here. Actually, I take that back. This is acetone, okay, so here's the acetone, and water. So again, they have very similar intermolecular forces, so they easily dissolve within one another. They're soluble within one another, and they completely mix to form a homogeneous mixture. So we call these miscible fluids. So here you can see that you can't see any discernible difference. So here's one phase here, and here's the line between the other phase here, okay? And so again, this line would represent the barrier between these two, okay? Okay. Now, we can also have gaseous solutions. So again, gaseous solutions are just one or more than one gas that are non-reactive. Okay, they got to be non-reactive, and they will mix together. So here's an example. I have gas A and gas B, or gas blue and gas red. And if we open up this little stopcock here so that the two can pass back and forth, again, as long as they don't react, they're going to mix at all proportions and form a homogeneous mixture. So eventually, the molecules are just going to move back and forth between the two until they form a homogeneous mixture. In other words, I have just as many blue molecules on this side that I have on this side. I have just as many red molecules on this side that I do this side. So again, they've formed our homogeneous mixture. Air is an example of a very complex homogeneous mixture. It's mainly composed of nitrogen at 78%, then oxygen at about 21%. Argon is actually the next most prevalent gas in our atmosphere at almost 1%. Carbon dioxide keeps climbing. I believe this is now 0.06%, and that's not good. I won't get into it, but who cares? This then is going to be continue to increase, and then there's a whole bunch of other gases. So the common ones would be water vapor, ozone, methane. Methane is produced by the rotting of organic material, so there's always methane being released. A cow, for example, when it farts, releases as much methane as 6,000 humans. So cow farts are pretty potent. Carbon monoxide is the result of incomplete combustion. Hydrogen's formed in a lot of chemical reactions that naturally occur. And then just a bunch of other gases. And then there's also a lot of, again, organic, right? Every time you use nail polish, for example, a lot of that acetone is evaporating, and it's evaporating into our ocean of air, and it remains there for long periods of time. Okay, we could also have solid solutions. Now, solid solutions are referred to as alloys. And so a couple of examples of alloys is brass. So brass is composed mainly of copper and zinc. Now keep in mind, in these alloys, there could be other elements also added to the material to either make it stronger or softer or more lustrous, more shiny or duller. But the main components for brass is copper and zinc. For pewter, which is kind of a gray colored material, it's zinc and tin. And for bronze, which again is kind of like that orangish material, it's mainly tin and copper. And of course, the orangish material of brass and bronze is coming from the copper, which is, again, got that orangish color, that copper color. Okay. Okay, so now let's get into the solubility process itself. Why do things dissolve in one another? Okay, so again, solubility simply refers to the amount of a substance that will dissolve in the solvent itself. And we're going to show a whole bunch of different ways. We talked about molarity and mass percent in Chem 110 and mole fraction as well. We're going to introduce a whole bunch of other ways now to express concentration. Okay, so many factors we're going to find out affect solubility, such as temperature. So this is true for, and we're going to talk about right now, we're just going to talk about liquid solutions that involve dissolved solids or gases. So for dissolved solids, we're going to find out that the temperature might cause more, a higher temperature might cause more of the salt to dissolve, or it might cause less of the salt to dissolve. In the case of gases, the higher the temperature, the less the gas can dissolve into water. And if we are dealing with gases dissolved in water, the pressure of that gas over the solution, the higher that pressure, the more dissolved in the solution. Okay? And we're going to have equations to quantify this stuff. So here's just an example. Let's say I have 100 milliliters of water, and I measure out 20 grams of sodium chloride, table salt. And I take that 20 grams and I throw it in the water and I mix it up. Well, it's all going to dissolve, okay? And we're going to form what's called an unsaturated solution. Unsaturated simply means I can dissolve more of that solute in there. And if we dissolve just a little bit, we're going to call it a dilute solution. But if we dissolved a lot of salt, we would call that a concentrated solution. Now, 20 grams, that probably puts us in between dilute and concentrated. That's quite a bit of salt. Okay, we're mainly going to deal with dilute solutions, but we're not putting nearly that amount of the material into our solvent. So again, excuse me. Again, unsaturated simply means that we can dissolve more of a particular salt in there. Okay. Now, there is a limit, though, to how much salt that we can dissolve in water. There's a limit to how much of anything we could dissolve in another solvent. at a particular temperature. So for example, if I try to dissolve 40 grams of salt this time in that 100 milliliters of water, so I'm going to throw the 40 grams in and I'm going to keep stirring and stirring and stirring until no more will dissolve. And what we'll find is that 4 grams of that sodium chloride did not dissolve. It remained a solid within the beaker itself. Okay, so basically we could say, we could call solubility, a lot of times solubility is given in grams per milliliter. So in this case, the solubility of sodium chloride in water at room temperature, and in fact, sodium chloride is kind of weird. It's pretty much temperature independent, and I'll show you later on a graph and why that is, okay? But we'll just say at room temperature, 36 grams per 100 milliliters. So that would be the solubility of sodium chloride in grams per milliliter of water, okay? So that is what we call a saturated solution. That means I can't get any more sodium chloride ions to dissolve and dissociate in this solution, okay? So again, saturated means, now this is going to be important because we're going to come back to this. So if I tell you we have a saturated solution, I'm basically telling you that we have the solubility of that solution. So later on, I'm going to ask you to determine the solubility constant. We're going to call it KSP, okay? It's an equilibrium constant. We'll talk about equilibrium in 2 chapters from now, okay? And so I'm going to ask you to determine the solubility constant of a given substance, and I'm going to tell you that it's saturated. Well, that's going to be a clue to tell you that, oh, okay, that's going to represent that KSP value because it is saturated. I can't dissolve any more in it, and I've dissolved everything I possibly could into the solution. So that's a saturated solution. Okay, now some salts, we could actually form an unstable solution called a supersaturated solution. Well, what is that? Well, let's look at sodium acetate, for example, okay? So this graph, for example, is not in your notes. So some things aren't in your notes because they're not that important that they need to be in your notes. But so here is a graph for sodium acetate. So this is just a salt. And we can see that at this line here would represent the saturated solution. So let's say at room temperature, I can dissolve approximately, what, about 75 grams of sodium acetate into 100 grams of water. Now, we'll assume that's, the density of water is approximately 1 gram per milliliter. So this is about 100 milliliters of water, okay? It has to be in grams because, of course, as the temperature changes, the density changes. So the volume would change. So we have to put it in grams, okay? So basically, again, at room temperature, we can dissolve about 75 grams. But now as I raise this temperature, let's say I raise it up to 100 degrees Celsius. Now I can dissolve, what, about 140 grams? So I can dissolve 140 grams. Now, for most salts, if I started to cool down the solution, all would happen is we would keep following this curve, and all of that extra salt that we dissolved at the higher temperature would immediately crystallize out and just precipitate out and fall to the bottom of the container, right? So any extra would have just fell out immediately upon cooling. That's true for almost all ionic compounds. Sodium acetate's one of the strange ones that can form these supersaturated solutions. So I heat the solution up, and I now dissolved 140 grams of sodium acetate into it, okay? Then I simply start to lower the temperature, but the salt doesn't come out. It remains. So I lower the temperature, but now at room temperature, I'm way up here. I'm in this supersaturated solution region where I now have more salt than I should have at that temperature, okay? Whoops. So these solutions are very unstable. So here's an example of a supersaturated sodium acetate solution. And if a speck of dust touches that solution, it's already unstable. It causes the extra sodium acetate to start to precipitate out. and it forms these really cool looking crystals. And those crystals are going to continue to form. They're just going to continue to form until all of the extra salt is crystallized out. And now what we're left with, this clear part here, is actually just a saturated solution at that temperature. So now the sodium acetate in this clear part of the solution is not going to crystallize out. But if we added any more solid sodium acetate to it, it would immediately crystallize out, because these crystals are going to give it a place to start to form the crystals. So the speck of dust just gave it some place to start forming a crystal. If your beaker's dirty, you can't do this, because whatever scratches there is on the glass will give the salt a place to start to crystallize. So you have to have really clean glassware, scratch-free, and then you can form these unusual supersaturated solutions. But again, we're not going to deal with supersaturated solutions. We're going to deal with dilute solutions. Now, let's talk about what solutes will dissolve in the solvent. And this, again, is going to be true for the solids that we dissolve and the liquids that we dissolve in one another, and to some extent the gases, but we're not going to get into the gases. The gases are different. We're going to quantify the gases, but not get into why one gas dissolves more than the other. But it does have a component of these intermolecular forces. So again, like dissolves like. And what that means is that solutes with similar intermolecular forces are going to dissolve solutes with similar intermolecular forces. And most of the time, you'll hear just polar solvents dissolve polar or ionic solutes. Well, that is the big part of it. And if you go into most chemistry, that's really all you need to know. Polar dissolves polar. Polar and non-polar do not dissolve. They're immiscible in one another, okay? Okay, so again, the polarity is going to be a major force of attraction, but hydrogen bonding is also going to be a factor as well. So polar molecules interact well with polar solvents, such as water. So for example, here we have hydrogen fluoride. Now, as you recall, hydrogen fluoride is a polar molecule because fluorine has a higher electronegativity than the hydrogen does. That means that the fluorine's pulling the bonding pair of electrons closer to it, making this side of the bond slightly negative. And now, because this is exposing the positive nucleus, it's slightly exposed, so it's slightly positive, right? And we draw a vector, a dipole moment, the arrow pointing towards the fluorine with the plus side on the hydrogen. Now, because there are no other bonds in this molecule, well, then they don't cancel, so it's a polar molecule, right? So we say that that's polar. In the case of the water, remember the water, the oxygen is much more electronegative than the hydrogen. So the dipole moment's pointing from the hydrogen to the oxygen and from this hydrogen to the oxygen. They're not equal and opposite, right? If they were equal and opposite like this, like carbon dioxide, those dipole moments would cancel and the molecule would be nonpolar, okay? In this case, it's bent. It's bent like this, so the dipole moments are going like this. So they're not, even though they're equal, they're not opposite, so they're not canceling. So there's a dipole moment going right up through the middle of that molecule. So water is polar. And the oxygen, again, is trying to pull the bonding electron, so it's going to be slightly negative. And the hydrogens, again, because the electrons are being pulled away from its nucleus, are going to be slightly positive. And so for a polar molecule, that means that the positive side is going to be attracted to the negative side of another polar molecule. And in this case, because we have this as our solute, well, it's going to interact well with the fluorine, right? Because that's the negative side and this is the positive side of the water. And the hydrogen, which is slightly positive, is going to interact or have a dipole-dipole interaction. That's what these dots represent. A dipole-dipole interaction with the oxygen. Now, in the case of hydrogen fluoride, it's even much stronger than you would expect just for the polar interactions, because both water and hydrogen fluoride display hydrogen bonding. Not a hydrogen bond, but hydrogen bonding. That's an intermolecular force. A hydrogen bond is a chemical bond. So here's a hydrogen-oxygen hydrogen bond. But hydrogen bonding occurs when you have a molecule that has an electronegative oxygen, nitrogen, or fluorine, and that electronegative oxygen, nitrogen, or fluorine has a lone pair. In this case, when you draw the Lewis dot structure for oxygen, for water, the oxygen has 2 sets of lone pair. And when you draw the Lewis structure for hydrogen fluoride, it has 3 sets of lone pair. So we have the electronegative oxygen, nitrogen, or fluorine. They have lone pairs. And the third criteria that you must meet is that the hydrogen is directly bound to the oxygen, nitrogen, or fluorine. So for example, an ether has an oxygen with 2 sets of lone pair, and the molecule probably has hydrogen in it. But in an ether, that oxygen is bound to 2 different carbons. So ether wouldn't display hydrogen bonding. It'd be a polar molecule, so thus it would have dipole-dipole interactions. And again, all molecules have London forces, okay? Now, nonpolar solutes interact with nonpolar solvents. So for example, octane and 3-methylpentane, these are both components found in gasoline. They are both just hydrocarbons, right? All they contain is carbon and hydrogen. Now we know that carbon-carbon bonds that are formed in the hydrocarbon, they got to be nonpolar because they both have the same electronegativity. And as you recall from Chem 110, the only bond that you were expected to know that didn't follow the criteria, right, the trend that, you know, fluorine is the most electronegative and francium is the least electronegative. So in other words, starting at fluorine, going down in group, the electronegativity decreases. And starting at fluorine and going left across the periodic table, the electronegativity decreases. So knowing those trends, you were always able to determine whether or not a bond was polar or nonpolar. But because hydrogen sits way over on the left, we generally think of hydrogen being much less electronegative than most of the other elements. But in the case of carbon, the electronegativity of carbon and hydrogen is nearly identical. So the one bond that you just have to memorize beyond those trends is that the carbon-hydrogen bond is essentially non-polar, and that's going to be really important, okay? So in a hydrocarbon, all we have is carbon-carbon, which are already non-polar bonds, and carbon-hydrogen bonds. And again, the carbon-hydrogen bonds are essentially non-polar. So these are non-polar molecules, therefore they don't have dipole-dipole interactions. And they can't have hydrogen bonding because they don't contain oxygen, nitrogen, or fluorine. So these are non-polar molecules. So they dissolve readily within one another. So non-polar molecules will dissolve other non-polar molecules. Now, when we have gasoline and water, so when we have octane and water, okay, the water has very strong, it has the London forces, the dipole-dipole interactions, and the hydrogen bonding. So the water molecules are holding on to each other very, very strongly. And the only attraction between the water molecule and the gasoline is London forces. So why are you going to break up these strong attractions amongst the water molecules to replace them with the weak London force attractions? So that's just not going to happen. So the polar solvent's going to remain attracted to one another and not allow the nonpolar solvent molecules to get inside. And so we say again, this would be immiscible. These two are insoluble because we have a non-polar substance and a polar substance. And again, the only reason the water is on the bottom here is because it has a higher density, 1 gram per milliliter, compared to gasoline, which is about 0.8 grams per milliliter. So the higher density always sinks to the bottom. Okay. So any questions thus far? And again, at any time, if you have questions, you need to stop me and ask. Okay. Okay, and so again, the net force is just pulling those water molecules into each other. So again, you're not going to break that. And again, we said gasoline and water, therefore, is immiscible. They do not mix. If they did mix, we'd call them miscible. Let's talk about the solubility of alcohols in particular. So again, here we have an alcohol. So this is ethanol. This is the one that's safe to drink. All other alcohols are not safe to drink. Okay, only ethanol. And again, we see here that ethanol will dissolve in water at any amount, you know, and that's because their intermolecular forces, again, are very similar. So again, we've already discussed that the oxygen has London forces because all molecules have London forces. I'll briefly explain that when I go over some sample problems here, if not today, tomorrow. And it has, it's polar, again, like we discussed, the dipole moments are pointing from hydrogen to oxygen, but because the water molecule is bent, it has an overall dipole moment, and therefore is polar, and it has hydrogen bonding. It has the electronegative oxygen, nitrogen, or fluorine. There are two sets of lone pair on the oxygen, and the oxygen is directly bound to a hydrogen. So it also has hydrogen bonding. Well, the same is true for the alcohol, right? The dipole moments pointing from, so this part of the molecule, though, is non-polar, right? All we have is carbon-carbon bond, which is non-polar, the carbon-hydrogen bonds, which are non-polar. So this part of the molecule is non-polar, but the alcohol part, we have a dipole moment pointing from the carbon to the oxygen and from the hydrogen to the oxygen. And again, this oxygen has a tetrahedral standard electron geometry, just like this oxygen did. But because we can't see the lone pairs, and there's two sets of lone pairs here, we have a bent orientation, a bent molecular geometry, right? And a bent molecular geometry. So for the same reason, this molecule ends up being polar, has London forces because all neutral molecules do, and it has hydrogen bonding. It too has an electronegative oxygen, nitrogen, or fluorine, which has a lone pair. In this case, it has two sets of lone pair, and has a hydrogen directly bound to the oxygen, or nitrogen, or fluorine. So it too has hydrogen bonding. So these two molecules have the same intermolecular forces. So in this case, ethanol will mix with any amount of water, okay? So here we go. Here's the ethanol. So it's completely miscible. I can dissolve any amount of ethanol in any amount of water. Same thing is true for propanol. So basically all we added was another CH3 over here. We removed one of these H's and replaced it with a CH3. Completely miscible. But now, once we get to 1-butanol, now all of a sudden it's not completely miscible. In fact, I can only dissolve 8.2 grams in 100 grams of water at 20 degrees Celsius. Can anybody tell me why that would be? Why did it all of a sudden go from miscible to now only partially soluble? Does anybody see it? Well, remember, like dissolves like. And remember, this part of the molecule is nonpolar. This part's polar, but this big part over here now is nonpolar. So now we got to break a whole lot more of the bonds between the water molecules themselves and replace it with these weak London forces. And as it becomes bigger, as this nonpolar portion of the molecule becomes bigger and bigger, less and less of the alcohol will actually dissolve. Because again, we got to replace more and more. So when we had the small molecules, we were just displacing maybe 1 or 2 of the hydrogen bonds of the water molecule that were forming with other water molecules. But now we're replacing lots and lots of those hydrogen bonds, hydrogen bonding within the water molecules of the solvent. And so the bigger this hydrocarbon end becomes, the bigger the non-polar part becomes, the less and less of the alcohol will actually dissolve into the water. Okay? Does everybody understand that? Everybody's good. Okay. So polar solvents such as water also interact strongly with ionic solids. And we talked a lot about this in Chem 110. So I'm just going to briefly review it again. Okay. So again, here we have sodium chloride. Sodium chloride is what we consider to be a strong electrolyte. That is, when you throw the solid sodium chloride, which consists of sodium ions and chloride ions, okay, and then in this big lattice to form a crystal, sodium chloride readily dissolves at any temperature in water to form a homogeneous solution. And the reason is, well, at first it doesn't make sense because we have a sodium chloride ionic bond. That is a chemical bond. They're very strong, right? 1,000 kilojoules per mole. Very, very strong. And for some reason, it's just dissolving in water. But the reason it's dissolving in water is it's forming another type of intermolecular force called an ion dipole interaction. Now, an ion dipole interaction might only be 20 to 100 kilojoules per mole. But that doesn't make sense. If the chemical bond was 1,000 kilojoules per mole, how am I breaking that to form something that only has 20 to 100 kilojoules per mole? Well, it's because I am forming a whole lot of them. So for example, in the sodium, the water molecule is polar, right? So the oxygen side is slightly negative, and it associates itself with the positive ions. And it makes a whole bunch of ion dipole interactions. The same thing is true with the anion, except this time the positive side of the water molecule is attracted to the ion. Again, forming a whole bunch of ion dipole interactions. Well, when you sum up the energies of all these ion dipole interactions, they are greater than the bond strength between the two ions. Those are our soluble salts. In the case of insoluble salts, this bond strength between the two ions is stronger than all of the ion dipole interactions that could possibly be made with the ions. And that's why they generally don't dissolve, or very, very, very small amount of it actually dissolves. So that's why ionic salt compounds will dissolve. If they're soluble, strong electrolytes, again, we're replacing the energy of that ionic bond with a whole bunch of ion dipole interactions between the neutral water molecules and the ions themselves. Okay. Okay. Let's now talk about what's called the heat of solution. So this is the enthalpy change of a solution. And so basically when a solid ionic compound is dissolved in water, it may absorb heat, it might release heat, or it might not change at all. In the case of sodium chloride, for example, table salt really it doesn't really absorb or release heat upon its dissolution. And so that's why sodium chloride is kind of unique in the fact that it will dissolve in ice water just as well it'll dissolve in boiling water, because it really isn't temperature dependent. And that's because its enthalpy of solution is nearly zero. But let's take an example of a hot pack. A hot pack is just an example of this heat of solution. A hot pack simply contains calcium chloride pellets. You're probably familiar with calcium. You're probably familiar with calcium chloride pellets. If you ever go to the store and you buy ice melt, and if they are little round white pellets, they're calcium chloride. If they look more like rock salt, it's sodium chloride. Okay, so it's just the calcium chloride, and there's a glass vial of water inside. And to activate the hot pack, all you do is you hit it with your fist. That breaks the vial of water inside, and it dissolves the calcium chloride. So the calcium chloride goes from a solid. You break the vial of water, and it dissociates then into the calcium and the chloride ions. And in the process, it's an exothermic process. this chemical reaction releases 83.3 kilojoules of energy. So it feels hot to you because you absorbed that energy, right? But the chemical reaction itself was exothermic in this case, and it released 83.3 kilojoules of energy, and the hot pack became hot. So that's one example of heat of solution. Now, the entropy of solution, we're going to talk a lot about this later on when we get into the chapter on thermodynamics. So in Chem 110, all we introduced so far is enthalpy, or the heat of reaction. We're going to talk later on about entropy. Entropy is a measure of disorder of a system. And generally, the entropy of dissolution is always positive, okay? Always positive. And that's because in this particular case, it's more complicated than this, and we'll get to that when we get into thermodynamics. But one of the things with thermodynamics is that it is more disorder, right? It's a measure of disorder. So if this is positive, that means the reaction went from being ordered to disordered. Well, here we can see it's nice and ordered. It's a single crystal all by itself. Once we threw it into water, it now dissociated into 3 different particles. So if a chemical reaction, if there's a more product molecules or ions than there are reactant molecules or ions, then we have an increase in disorder because the number of particles increased. And so in the case of dissolution, dissolving a substance in water, the entropy change is almost always positive, okay? Okay, now we could also have a cold pack. Well, again, a cold pack is, again, just a salt dissolving in water. In this case, it's ammonium nitrate. Again, they're just little white pellets inside there, but it's ammonium nitrate. And again, a glass vial of water. And when you take and break that glass vial of water, the solid ammonium nitrate dissolves and forms ammonium ion and a nitrate ion. Okay, again, a strong electrolyte, so it completely dissociates into the ammonium ion and the nitrate ion. And in this particular case, it absorbs energy from the surroundings. It absorbs 25.7 kilojoules per mole of ammonium nitrate dissolved. And it's absorbing that energy from you being the surroundings in this case, and so the ice pack feels cold because it's taking energy from you. Okay? So again, this is just what the heat of solution is. So this is called the heat of solution or dissolution. Okay? So the heat of dissolution is the same thing. Also called solvation. It has a lot of different names. Okay? Okay, now let's look at these solids. So, for example, most solids, most ionic compounds, when you dissolve them in water, their solubility increases with temperature. So we already seen that with the sodium acetate, right? Well, that's also true for potassium nitrate and copper 2 sulfate. As I increase the temperature, so at 20 degrees, I can only dissolve about, 30 grams of potassium nitrate per 100 grams of water. But as I increase the temperature, let's say to 100 degrees, now all of a sudden you can see I can dissolve 200 grams of potassium nitrate for every 100 grams of water. Now in the case of potassium nitrate, if I cool it down, that extra potassium nitrate immediately solidifies and forms a crystal and falls to the bottom. It won't form a supersaturated solution like the sodium acetate. Again, there's very few ionic compounds, there's very few salts that will actually form supersaturated solutions. Potassium nitrate, copper 2 sulfate are not those solutions. Then I said sodium chloride basically is unaffected by the temperature. In very cold water, you can dissolve just about as much as you can in hot water. So we can see that the enthalpy of the enthalpy of these solutions, again, if you, I won't get into that. But again, we can see that sometimes the more will dissolve, sometimes it's unaffected by temperature. And for certain salts, the higher the temperature, the less you can dissolve. And that has to do with the crystal structure of the salt that's formed. At higher temperature, the crystal structure actually changes. In this case, it changes twice and it actually forms a more stable crystal. The crystal collapses in on itself. And as you remember, one of the important things with ionic bond strength, the first thing, of course, was the absolute difference in charge. So if you have a +2 and a -2 ion, that would be a total difference of 4. That's much stronger than a +1 ion and a -1 ion, which has a difference of 2. So the +4, the bigger the difference in the charge, the absolute difference, the stronger the ionic bond strength. But the second factor was how close the size, right? How close the ions were to one another. The closer they are, the stronger the ionic bond strength. Well, in this case, as you're heating it up, it's causing the crystal to change structure, and the ions start to get closer to one another. And because they get closer to one another, well, those are stronger and less will actually dissolve. And then there's actually a second structural change, and even less dissolves at higher temperature. Okay. So let's talk about the temperature effects on gases. So the solubility of gas dissolved in a liquid always decreases as you increase the temperature. So the colder the liquid, the more gas will dissolve in it. The higher the temperature, the less gas, right? You can test for that. Think about a carbonated beverage. It stays carbonated at colder temperatures for longer periods of time. But as soon as the ice melts and it heats up, all of a sudden it goes flat. And that's because the solution can hold less carbon dioxide at higher temperatures. Okay. So, and I just gave you that as an example. Okay, so let's look at this here. So we have a cylinder here, and it's closed off with a piston. And at the bottom of the cylinder, we have water. And then above it, we have just pure carbon dioxide gas. Now, some of those carbon dioxide gas molecules have actually dissolved into the solution, represented by the little black dots in the solution itself. Okay? But if we increase the pressure, we can force those gas molecules into the solution. Okay? That's Le Chatelier's principle. Le Chatelier's principle basically says that whatever you do to a system in equilibrium. So what does that mean? Well, in equilibrium means that we have a certain amount of gas molecules above the water, and we have a certain amount of gas molecules in the water. And this is actually a dynamic process. Some of these gas molecules are escaping back out into the gas phase, and some of these molecules are going back and getting stuck and then finally going into the liquid. Well, when the number of gas molecules going back into the liquid equals the number of molecules, the rate, right, at which these are occurring, equals the rate at which these molecules are escaping, well, we call that equilibrium. And it looks like the numbers are not changing anymore, even though they are constantly. It's just that the number going in is equal to the number coming out at any given time. So we call that equilibrium. So Le Chatelier's principle simply says, whatever we do, whatever external change we make, nature's going to try to undo it. And it's going to do that by shifting the equilibrium of the chemical reaction. And we're going to get into this in really big detail in 2 chapters. So if I increase the pressure inside here by simply pushing down on the piston, right, reduce the volume, increase the pressure, right, that's just Boyle's law. Now what's going to happen is that to reduce the pressure, right, I changed the pressure. To reduce the pressure, nature is going to absorb more of those carbon dioxide molecules into the solution until we reach this equilibrium again, where the number of carbon dioxide escaping is equal to the number of carbon dioxide going in. You can think of this in the terms of the kinetic molecular theory as well, right? When we reduce the volume, the molecules now don't have as big as a difference, right? This guy would have to, if it was going in this direction, right, it'd have to go the whole way up to the top, bounce off of this, come back down and hit the liquid, and maybe have a chance of getting absorbed into the liquid. But when we reduce the volume, now it's hitting the liquid striking the liquid much more often, giving it a much better chance to be absorbed into the solution. Okay? But the important takeaway here is Le Chatelier's principle. Any change we make in a system, nature's going to try to undo it, and it does that by shifting the equilibrium of a chemical reaction. In this case, because I increase the pressure of the gas, it's going to try to push more of those gas molecules into the liquid to reduce that pressure that I just increased. We can actually quantify this using what's called Henry's law. So Henry's law says the solubility, and this solubility can be given in either grams per liter or moles per liter. It depends really on what field you're in. In chemistry, it's almost always going to be moles per liter. Engineering, and oftentimes in biology, it's going to be given in grams per liter. Okay? And again, depending on what your field is, what you specialize in, you'll use different units. But that is the solubility. It's just the amount that can be dissolved in a certain volume. The amount of gas, right? So this is going to be the moles of gas or the grams of gas. And this is going to be the liters of solution. This KH, so the K subscript H, is what's called Henry's constant, or Henry's law constant. Okay, so Henry's constant again is different for each gas and each solvent at each temperature. Okay, so just having carbon dioxide and water will have an infinite number of Henry law constants because it depends on the temperature. So we'll always be working at 20 degrees Celsius, right? Because the table that I give you, which is in the tables of chemical data, or in your book, but I believe in your book it's in one of the chapters. And that's why I transferred them all to that one file, so you don't have to try to keep switching through the book to find out where the tables are. So they're now all in those tables of chemical data posted on Canvas. And I believe they're all at 20 degrees Celsius. And then P is just the partial pressure of the gas over the liquid. Okay, so that's just the partial pressure of the gas over the liquid. So there we have mole fraction. Then another mole percent. So mole percent, all you're going to do is take the mole fraction and multiply that by 100%. That's normally what we have with percentages. Then we had mass percentage, which again, we've already seen all of these equations. So mass percent, and again, mass percent is going to be a component of a mixture. So again, if that mixture or compound has, A, B, and C in it, we would just take the mass percent of one part. So in this case, let's say A. So then that's just going to be the mass of A. Now that's all the A that's in it. Okay, that's all that component. And then we're going to divide that by the total mass. So that's going to be the mass of everything. In this case, we're talking about solution. So this would be the mass of the solute. And this would be the mass of the solute plus solvent, right? So that would be the whole thing. And then times 100%. Now, if we start to get into dilute solutions, we then end up with what we call parts per million, or ppm. And parts per million is basically, it's the same thing, right? It's the mass of the one component that you're interested in divided by the total mass. But this time, instead of times 100, it's going to be times 1,000,000. And so that's going to be parts per million. And there's parts per billion, which again is the mass of that one component divided by the total mass. And you're simply going to multiply that by 1 billion, 10 to the 9. And there's actually parts per trillion too, which would just be same thing, but times 10 to the 12. Okay, we're only going to go up to parts per billion. Then there's the new type of concentration, which we called molality. And molality, the only variable I'm going to use for molality is, again, the C, and then a lowercase m representing molality. And that is just going to be, again, the moles of the solute. So moles of solute, which again, the variable would be N. And then we're going to divide that by the kilograms of solvent, which would be a mass. But again, now notice that this is just solvent, but for molarity, it was the whole solution. Okay, so that's the difference between these two. okay? Then we talked about gases dissolving in a solution, and for that we used Henry's law. And so Henry's law simply indicated that the solubility, so that's S, so the solubility, and that's either going to be in grams per liter or moles per liter, and it was equal to a proportionality constant, okay, a proportionality constant that we called Henry's law constant. That constant is unique for every solvent-solute combination, and it's temperature dependent, okay? So again, you'd have to look that up for every solute-solvent combination and at a given temperature. And then that is just proportional then, the solubility is proportional to the partial pressure of the gas that you're dissolving in the solvent. So that's the partial pressure of the gas that you're dissolving in the solvent, okay? Then we had Raoult's law that talked about the vapor pressure of a solution, and how that when you add an involatile, right? So we have two, Raoult's law. So so again, this is the measuring the partial pressure of a solution, and we have two of them. We have one for a non-volatile solute. And in that case, the vapor pressure of the solution was equal to the vapor pressure of the pure solvent times the mole fraction of the solvent. Then if the solute was volatile, in other words, it would evaporate, okay? So again, non-volatile solute, they don't evaporate appreciably, okay? Everything evaporates. Okay, your computer right now is evaporating in front of you. Now, it might take a few billion years for it to completely evaporate, but it is evaporating, okay? But so we're going to consider that to be a non-volatile solute. If you put something on your desk and it evaporates considerably within a day, we would consider that to be a volatile solute. So most liquids, of course, are volatile solids. Some solids are actually volatile. Okay, but we're going to mainly say that the liquids are volatile and the solids are going to be non-volatile. Okay, so now the vapor pressure of that solution is not only have a contribution from the vapor pressure of the solvent, which would be the same as we've seen before, but now we got to add on that contribution of the solute. So this would be the vapor pressure of the pure solute times the mole fraction of the solute. Okay. Okay, next, we haven't talked about this yet. We'll talk about this later today, but we're going to talk about some other colligative properties, and one will be the boiling point elevation. So that is whenever you dissolve something into a solution, it is going to cause the boiling point to become elevated higher, okay? So if you add salt to water, instead of water, again, this would all be at sea level, instead of water boiling at 100 degrees Celsius, it's going to boil at some higher temperature. And that's going to be, so this now is the change in the boiling point. So be careful. If I ask you what's the new boiling point, you would have to add this value to the original boiling point, okay? And so that is just going to be equal to I, and we're going to talk about this today. That's the Van Hoff factor. Remember, colligative properties only matter how many particles there are, not what they are. And so we'll see that I represents the number of particles for each particle we put in. If it's a molecular compound that doesn't dissociate, I is simply going to be 1. But if it's an ionic compound, a strong electrolyte, Its I is going to depend on how many ions are formed when you dissolve that one particle in solution. So that's the Van Hoff factor. And then there's a proportionality constant. And so this is the boiling point elevation constant. It is only dependent on the solvent, okay? It is only dependent on the solvent. Doesn't matter what the solute is. That's the idea of a colligative property, okay? And then it's going to be the mole concentration, okay? So this is the mole concentration. Similar, we're going to see something with a freezing point. We're going to see a freezing point depression. So the freezing point will be lowered whenever you add something to it. And again, this is the change in the freezing point will be equal to, again, that Van Hoff factor. Then again, each solvent will have its own freezing point depression constant. And again, times the mole concentration of that solution. Then we have the osmotic pressure. And the osmotic pressure, we give a variable of pi. So that's the osmotic pressure. And it is going to be equal again to the Van Hoff factor times the molar concentration. So that's now a capital M. These are lowercase m's, and this is a capital M. Okay, and then that's going to be times the molar gas constant. And that molar gas constant, in this case, is going to be the 0.082058 atmosphere liter per Kelvin per mole. Again, those you should already know from Chem 110. And then T is going to be the absolute temperature. Believe it or not, this equation is derived from the ideal gas law. And so that has to be the absolute temperature. Okay. Now, the constants that you need to know, you should have already learned them from Chem 110. Avogadro's number. So,
Dr. Bell, I have a quick question.
Yep.
The absolute temperature, that's in Kelvin, correct?
That is correct.
Okay, just want to double check. Thank you.
That is in Kelvin. And then we have Avogadro's number, which we give the variable. Again, all the variables are italic. I can't write italic. So that's N subscript capital A, not to be confused with Na, which would be sodium, okay? So Avogadro's number, 6.022 times 10 to the 23rd, and it has units of per mole. Just like there's 12 per dozen, well, there's 6.022 times 10 to the 23rd per mole. And then the two molar gas constants that we're going to use again throughout the course, the one being 0.082058 atmosphere liter per Kelvin per mole. And then the other one we're going to use is the 8.3145 joules per Kelvin per mole. And again, which one you use really depends on the unit. So when you learn these, you should have learned them with their units. That way you know exactly which one that you have to use. And then, of course, the joule, a lot of times we have to convert it, and 1 joule is equal to, you can think of this, right? We know that kinetic energy is equal to 1/2 the mass times the velocity squared. Well, the mass, the SI unit of the mass is a kilogram. The SI units of velocity are meters per second, but they're squared, so it's meters squared per second squared. And so there is the conversion between joules and kilograms. Also, for those who didn't have me in Chem 110, remember a per second is just 1/a second. A per mole is just 1/a mole. And we're going to see this a lot. We're going to see 1 some per. Well, that really is 1/1 a mole, which if we multiplied this then by 1, right? Because a mole divided by a mole is 1. So we didn't multiply this by anything. But if we look at the denominator, the moles cancel. And so that is just equal to moles. So again, we'll see this a lot. And in the next chapter, when we start talking about kinetics, following the units is going to be important, and you're going to see it can be challenging. Okay, so understanding all this is going to help. Okay, now that is all of the equations. We haven't talked about basically anything on this page, and we'll do that later today. Any questions about any of that good stuff? Okay, everybody good. Okay. Can't believe my camera died. Okay, so let's start then. We're going to start now. All the problems I'm going to do in what we would normally call recitation is going to be the homework problems that I've posted on Canvas. So again, these are all homework problems I've written and provided solutions for. And so these numbers are coming from the homework problems I posted on Canvas. So this is number 10 from chapter 13. And it says, arrange the following substances in order of increasing solubility in water. So water, so we have H2O. Now we know that solubility like dissolves like. And so in order to understand that, we need to understand what intermolecular forces are. So as a quick review, there's different types of intermolecular forces. Now, again, these are much weaker than chemical bonds, ionic bonds, covalent bonds, metallic bonds. So they're much weaker than those regular bonds. So first we have London or dispersion forces. Again, these are all the intermolecular forces. So London forces, what happens is, let's say we have a couple of, let's say, helium atoms, right? So there's our nucleus that has 2 protons in it. Here's another helium atom. It has 2 protons in it. And again, this could represent a whole molecule. Molecules have, nuclei with protons, and then they're surrounded by electrons. Okay, so these electrons are just randomly moving all around the atom. Now, at any given instant, these electrons might have moved to the one side of the atom. Well, basically what that means is that because we got the negative side over here, this side is slightly negative. And now you can see we have the exposed protons in the nucleus. So this side is slightly positive. Now they're not full positive and negative charges like we see with ions. Okay. But what that does is that now this positive charge attracts the electrons from a neighboring molecule or atom. And so what occurs then is that we induce a dipole on the neighboring molecule or atom. So now this side is slightly negative, this side slightly positive, this side slightly negative, and this side slightly positive. Well, now we have an interaction, an attraction between the two. These, of course, are the weakest of the intermolecular forces. And these increase with increasing mass of your atoms or molecules. Well, why is that? Well, because as you increase the mass, basically what you're doing is increasing the number of protons and electrons, which means the bigger difference in charges that you can get, which means a stronger interaction between the two. But again, these are the weakest of the intermolecular forces. Then you have dipole-dipole interactions. Okay, can't spell. Wow, that's interactions, okay? Or dipole-dipole forces, right? So now if you have a polar molecule, so let's say we have ammonia. So ammonia is a trigonal pyramidal molecule. And so it has hydrogens, it has a lone pair up here. And of course, the dipole moments are all pointing towards the nitrogen. So we've lost symmetry because of that lone pair. And basically what that means is that we have a net dipole moment going up through this molecule, okay? So this side again now is slightly negative and this side is slightly positive. So if I redraw that, let me redraw that like this. And let's say we have another polar molecule. Let's say we have, so again, we have our dipole moment going through the molecule like this. So this side is slightly negative, this side slightly positive. And let's say we have another polar molecule. Let's say hydrogen chloride. So again, for hydrogen chloride, the dipole moment's pointing towards the more electronegative chlorine. And so this side is going to be slightly positive. This side is going to be slightly negative. Okay, so again, we have this negative attracting this positive, and there is the force of attraction. So that's the dipole-dipole interaction. Okay, so that's that force of attraction. This tends to be, again, we're going to always be dealing with small molecules. For large molecules, the London forces could be greater than the dipole-dipole interactions, but we're going to deal mainly with small molecules, in which again, we would assume that the dipole-dipole interactions are going to be greater than the London forces. But again, remember that these could be greater for larger molecules. Okay? Okay, so next we have the hydrogen bonding. Now this isn't a hydrogen bond, that's a chemical bond. This is hydrogen bonding with that ing. This is hydrogen bonding. Another intermolecular force, okay? And with hydrogen bonding, you have a requirement. You have to have an electronegative oxygen, nitrogen, or fluorine. That electronegative oxygen, nitrogen, or fluorine must have a lone pair, and hydrogen must be directly bound, covalently bound to the oxygen, nitrogen, or fluorine. So for example, we have a water molecule, right? So water molecule has 4 regions of electron density. It has 2 hydrogen bonds, and this is approximately 109, a little bit less than 109 because of the lone pairs that are hanging out over here, right? We have a lone pair here, a lone pair over here. And so this side, we have those lone pairs, and then the hydrogens on this side. Now, because this thing is so electronegative, these guys are really positive, much more so than we've seen with the dipole-dipole interactions. And these, of course, are negatively charged. So let's say we have another molecule. So we can see this displays hydrogen bonding because it has an electronegative oxygen, nitrogen, or fluorine, has a lone pair on that oxygen, nitrogen, or fluorine, and hydrogen is directly bound to the oxygen, nitrogen, and fluorine. So let's say we have hydrogen fluoride then. Oops. Well, again, we can see we have the electronegative nitrogen, hydrogen, or fluorine with a lone pair directly bound to a hydrogen. Okay. Now again, the hydrogen is going to be extremely positive, and we got the lone pairs over here. So what we see is a direct interaction between those lone pairs and the hydrogen, between those lone pairs and a hydrogen. Okay? So that is hydrogen bonding. Okay, any questions about the intermolecular forces? Hi, Jada. Please turn your camera on. Have your mic ready. No, she didn't hear me yet. Hi, Jada. Please turn your camera on and have your mic ready. My camera died about 2 minutes ago or 5 minutes ago, so that's why you don't see me. Hopefully I'll get that fixed at some point here. Okay, so no questions about intermolecular forces. So this, again, something you should have learned from Chem 110, was really important. Okay. And then Jada, go ahead and mute your mic. Okay. Okay, so now that's important because when we try to answer this question here, it says arrange the following substances in order of increasing solubility in water. Well, we have to understand the intermolecular forces with each one of these, okay? Now, we've already seen that the water looks like this, right? So we have to draw the proper perspective drawing, the three-dimensional Lewis structure, right? That's the perspective drawing of water. So again, now I'll go through this real quick, but again, this is all Chem 110. You should have already learned this. So go back and review it if you don't know how. But you need to draw your Lewis dot structures, and you need to do it relatively quickly. Well, I'll tell you, when all you have is period 2 elements, it's actually kind of easy. So the period 2 elements, of course, are these guys right here. So particularly carbon, nitrogen, oxygen, fluorine. And we know that hydrogen being in group 1 and only having 1 electron and 1 s orbital available for bonding can only ever form a single bond and has no lone pair, okay? So again, we can see that, right? So hydrogen is in group 1, right? We can see that from the periodic table. Hydrogen is in group 1. And therefore, it only has 1 electron, which will draw a Lewis dot structure like that. So it's only ever going to form a single bond, no lone pairs. When we go to boron, so we're just going to skip over. I'm going to skip helium because we know that helium doesn't. And I'm going to skip lithium and beryllium because we're never going to deal with them. But boron, we might. And boron being in a period 2 element, remember the period 2 elements, the quantum numbers, if n equals 2, L, the azimuthal quantum number, can only, or angular momentum quantum number, can only be 0 up to n minus 1. So that means for period 2 elements, all I have is L equals 0 and 1, which means it's an S and a P subshell. Well, an S subshell can only ever have 2 electrons, therefore form 1 bond. And the P subshell has 3 p orbitals, which can only hold 2 electrons each or make 3 bonds, okay? Or could hold a set alone pair, right? So boron, being in group 3, main group element, has 3 electrons. So I'm going to write it like this: 1, 2, 3. According to Hund's rule, I'm going to fill them singly and only pair them up when I have to. So we can see boron is going to form 3 single bonds and not have any lone pair. Carbon, being in group 4, has 4 valence electrons. So you can see carbon is going to form 4 bonds and not have any lone pairs. Now it can form 4 single bonds, or we might use both of these for a double bond, or all 3 of these for a triple bond. But in the end, it only forms a total of 4 bonds, whether it be 4 singles, 2 singles and a double, 2 doubles, or a single and a triple. It's going to form 4 bonds. Nitrogen, being in group 5, has 5 valence electrons. So 1, 2, 3, 4, 5. So you can see nitrogen is going to form 3 single bonds and have a set of lone pairs. Oxygen, being in group 6, 1, 2, 3, 4, 5, 6. You can see oxygen is going to have 2 sets of lone pair, and it can form 2 bonds, 2 single bonds or 1 double bond. Okay, and then the fluorine, being in group 7, has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. So you can see that fluorine, and most halogens for that matter, are going to have 3 sets of lone pair, and it's going to form 1 single bond. So this is the way the period 2 elements always behave, okay? That's the way these guys always behave. So now, of course, formal charges dictate whether or not it is the most probable structure or not, okay? But this now is going to allow us to draw Lewis dot structures very, very quickly. So again, if I have water, well, I have the oxygen, and I can see already that it has 1, 2, 3, 4. Now I know that I'm going to have 2 single bonds because of the hydrogens, right? So I'm going to have 1, 2, 3, 4 regions of electron density. That means that the oxygen has a tetrahedral electron pair geometry, standard electron geometry. I'm going to put the lone pairs here and here because it just makes it easier when you're trying to evaluate whether or not the molecule is polar or not. And then the hydrogens I'll just put here and here. And we know, of course, this bond angle is about 109.5. We also know, again, that the oxygen is much more electronegative than the hydrogen. So we got those dipole moments. Now, those dipole moments are equal in magnitude, so they should be the same length. Now, the lone pairs do contribute to the overall polarity of a molecule in a relatively complicated way, but luckily we could just ignore it. If all we're worried about is whether or not the molecule is polar or nonpolar, we can simply ignore those electrons. Now we've lost symmetry. We lost symmetry because of these lone pairs. And again, these dipole moments are not pointing directly at one another. So that means we end up with a net dipole going through the molecule that looks like that. So this molecule then is polar. Now, once we've done that, we can now establish what the intermolecular forces are. It has London forces because all neutral molecules have London forces. By the way, these intermolecular forces that I've talked about so far, now we also talked about ion dipole interactions. But for the London forces, dipole-dipole interactions and hydrogen bonding can only occur for neutral molecules, okay? So it has London forces. Now they're going to be the weakest. The molecule's polar, so it has dipole-dipole interactions. And we have an electronegative oxygen with a lone pair and a hydrogen bound directly to it. So this guy has hydrogen bonding. And again, this would be the dominant force, although these are additive, okay? So it has all three and they add. Okay, so there's our solvent. Then let's look at the first compound. We have methanol. So again, we have 2 central atoms this time. We have a carbon and an oxygen. The carbon, again, we know that the carbon, again, is going to be like this, and 3 of these bonds will be the hydrogen, and another one will be to that oxygen. So these are called structural formulas. It's kind of telling you what the central atoms are and what's bound to what. So if we have this part here, which again, the carbon would be tetrahedral. So again, it would look like this. I'll make these the hydrogen, and then that's bound to an oxygen. Now the oxygen, again, as we can see, has 4 regions. Now, because we know it's not going to form any double bonds, right? We already have a single bond here, and we know the hydrogen's got to make a single bond. So it's going to be 2 bonds and 2 lone pairs. So that's 4 regions of electron density. So that's a standard electron geometry, again, tetrahedral. So that again would look like this. Okay, we'll put the lone pair here, and then the hydrogen will go right here. Okay, any questions about that? Okay, now one thing I forgot to talk about is formal charges, right? So again, the easiest way to do formal charges, for example, carbon's in group 4, so it has 4 valence electrons. We're going to subtract 1 for each bond. And if there was lone pairs, we'd subtract 1 for each lone pair. So if this is 4 minus 1, 2, 3, 4, that has a formal charge of 0. Hydrogen being in group 1, 1 minus 1 is 0. And of course, all these hydrogens only have a single bond, so they're all 0. The oxygen being in group 6, minus 1, 2, 3, 4, 5, 6. Well, that's 0. And of course, the most probable structure has the fewest non-zero formal charges. In this case, they're all zeros, so this would be the most probable formal charge, most probable structure. Now, also keep in mind that you cannot violate the octet rule for these period 2 elements because there's no available d orbitals. And that's how we violate the octet rule. Now, for period 3 and beyond, we can violate the octet rule by having more than 8 electrons around the central atom. My point is that sometimes you have to have non-zero formal charges on period 2 elements because you can't violate that octet rule for them. Again, go back and try to do some of these Lewis dot structures if you forgot all this stuff. Okay, so now, as far as polarity of the molecule is concerned, well, we know that the carbon-hydrogen bond is non-polar. Okay, we just have to memorize that. That's the only one you have to memorize. The rest of them, we could just go by the trends in electronegativity. So again, we know that fluorine, we're going to ignore the noble gases. We're going to assume that they're just have zero electronegativity. It's actually not true, which is kind of weird, but we're going to assume that they have zero. And fluorine then is going to be the most electronegative element, and francium is going to be the least. So we can see that the electronegativity decreases going down a group and decreases going right to left across the period. So from that, we could always find what is the most electronegative element. Now, I would never give you a compound on an exam that is, let's say, contains oxygen and chlorine and then ask you which one's the least electronegative. The reality is it drops faster this way, so oxygen is actually more electronegative than the chlorine, okay? But again, I'm not asking you to know that. Okay, so that means that the oxygen is more electronegative than the hydrogen, so the dipole moment is pointing towards the oxygen. And again, the carbon is less electronegative. The carbon is less electronegative, again, as we can see. Here's oxygen, carbon's to the left of it, so it's less electronegative. So again, the dipole moment is pointing towards the oxygen. Now, because those two dipoles aren't pointing, they're at an angle like this, they're not canceling, and so there's actually a dipole moment going right down through this part of the molecule, okay? Okay, so we know that this molecule is polar. We've also established then that this part of the molecule that contains the carbons and hydrogens only does not contribute to the polarity of the molecule, and in fact would only have London forces. But this molecule overall has London forces because it is a molecule. It has protons and electrons. It's a polar molecule, so it has dipole-dipole interactions. And we have an electronegative oxygen, nitrogen, or fluorine with a lone pair directly bound to a hydrogen, so it has hydrogen bonding. And of course, again, the hydrogen bonding would dominate in this particular case because it's a small molecule. But now let's go to the next one. This one here is diethyl ether. Now, I've already seen that the carbon parts, they aren't going to contribute to anything, so I don't really care about them. I can see this carbon, right? This carbon is going to have 4 bonds. It's going to have 4 bonds. 3 of them are going to be hydrogen, and the other one's going to be to that carbon. So again, I don't really need to worry about that one then. I'm just going to write it like that. Then this carbon, again, is going to have 4 bonds. 2 of them will be to these hydrogens. 1 is bound to this carbon, and the other is bound to that oxygen. So I'm just going to write it like this. I'm not even going to write a perspective drawing because, again, it really doesn't matter. These are the hydrogens. Now I have this oxygen. Well, oxygen can form a double bond and have 2 lone pairs, or 2 single bonds and have 2 lone pairs. In this case, that oxygen is bound to this carbon, and it's going to be bound to that carbon, and it's going to be tetrahedral. And so, again, it's bound to this carbon, which, again, it too is tetrahedral, and then is bound to that other CH3 group. And again, I don't care about this part, right? Because those are non-polar. We know that the carbon-carbon and carbon-hydrogen bonds are non-polar. So we don't need to worry about that. But what I do see here is that I have the oxygen, which is more electronegative than the carbon. And again, if you do the formal charges, which I suggest you do, okay, you're going to find out that they're all zeros again. And then we have this dipole moment. Now again, this is tetrahedral, so this is 109.5. So again, it's bent and not straight. So the dipoles aren't canceling. So we have a dipole moment going up through the middle of this molecule. So this molecule is polar, okay? Okay, so now for intermolecular forces. Now, once we've drawn that perspective drawing, determined the molecule's polar or non-polar, I can now start determining the intermolecular forces. Again, of course, it has London forces because it is a molecule. It is polar, therefore it has dipole-dipole interactions. And so, Hannah, does this molecule display hydrogen bonding?
It does not display hydrogen bonding because the lone pairs on the oxygen, there are lone pairs, but then the oxygen itself isn't bound to the hydrogen.
Exactly, right. We meet two of the criteria. We have an electronegative oxygen, nitrogen, or fluorine. The electronegative oxygen, nitrogen, or fluorine does have lone pairs, but there's no hydrogens directly bound to this oxygen. So therefore, there is no hydrogen bonding. So that's why you got to draw the Lewis dot structure. Okay, so there is no hydrogen bonding. Okay, so now in this particular case, you don't need to know this, but the dipole is actually fairly weak. And it's actually the London forces are stronger. But if I asked you, you're just going to say the dipole-dipole interactions are stronger. Okay, do I need to draw, so Leah, do I need to draw the Lewis dot structure for this compound?
I wouldn't say so because technically you just connect all the carbons together, then on each side of carbon there's a hydrogen.
Right, so is it going to be polar?
Actually,
I mean, remember, we're worried about two things for intermolecular forces. Is the molecule polar, and will it display hydrogen bonding? So is that molecule polar? Is a carbon-carbon bond polar? Because it's going to form carbon-carbon bonds, right?
yeah, but if symmetry killed polarity, then it won't.
Well, wait a minute. We have this, right? So basically, we're going to have a whole chain of this, and there's going to be hydrogens all over the place.
So wouldn't it be symmetrical?
Not going to be symmetrical.
Oh, it's not. Okay, then it's polar.
Okay. Well, no. Well, that's what we need. What is there a dipole moment between these two carbons? Is there a difference in electronegativity between these two carbons? No.
Yeah.
So no dipole moment.
Okay, so no.
Is there a dipole moment between the carbon and the hydrogen?
Yeah. It's going to carbon.
Everybody agree?
Am I wrong?
Does anybody disagree? Is the carbon-hydrogen bond polar?
It is not polar.
It is not. And how do you know that, Keenan?
Just we know that the carbon-hydrogen bond is not polar.
Again, remember, I keep saying this over and over and over again. The carbon-hydrogen bond is not polar. It's the only one I want you to memorize. It's the only one. So if the carbon-hydrogen bond isn't polar and the carbon-carbon bond isn't polar, Leah, is this molecule polar?
Not polar.
Not polar because we don't have any polar bonds. So therefore it can't be polar, right? So this molecule isn't polar. And will it display hydrogen bonding, Leah?
Oh, it is going to not.
Why not?
Well, firstly, I don't think there's going to be a lone pair, and there's no hydrogen bounded to an oxygen, nitrogen, or fluorine.
You're absolutely correct. Here's an easier way to look at it. There's no oxygen, nitrogen, or fluorine.
Yep,
Right?
that's it. That's it.
Yeah, so boom, right there alone, it's done. It can't have hydrogen bonding. So I don't even need to draw the structure of this. So again, recognizing that's going to save you a lot of time. So is it Katrine? Your mic's muted. You got to unmute your mic.
It's Katrin.
Katrin. Okay, Katrin. Katrin. Okay, Katrin, what are the intermolecular forces going to be on octane?
London dispersion.
Okay, so London or dispersion forces. Dipole?
No.
Nope, because this molecule, as we've already established, is non-polar. Okay. Is it going to have hydrogen bonding?
No.
No, again, we have established that. So it only has London forces. Okay, Keenan, can you tell me then, so I want to arrange these in increasing solubility. So what I suggest you do is you go increasing.
So we're going weakest to strongest.
The weakest to strongest, or lowest to highest.
Yeah. So would it go, the CH-H18 would be the weakest, followed by the CH3, CH2, CH2, CH3, followed by the CH3HO.
CH3HL?
HO.
HO, okay, I'm sorry, OH.
Or
Okay.
OH. Oh, sorry.
No, that's okay. I'm already confused. I don't need any help. CH3, CH2, O, CH2, so the ether. So this is
Yep.
just diethyl ether, commonly known as ether.
Okay.
The octane, the ether, then you said the methanol, and
Am I just going with these three or the ones, all of them?
1, 2, 3. Oh, we're missing 2 more.
We're missing 2.
Shit. Okay. Okay. So let's go to this one next. Okay. So we have ammonia, NH3. So again, looking at this, we have nitrogen. So there's, again, we're going to form 3 bonds with a lone pair. Well, we see it's NH3, so 3 of those bonds are going to be hydrogen. Now that's 1, 2, 3, 4 regions of electron density. So that means it has a standard electron geometry of tetrahedral again. So that's going to look like this. I'll just put the hydrogens here, and this will be the lone pair up here. Again, we see that the dipole moments are all pointing towards the more electronegative nitrogen. Again, they're like this. They're not pointing directly at one another. They're like this, so they're not canceling. So this molecule has a net dipole moment. Again, I don't care that you know where to draw the net dipole moment. I need you to understand that this molecule is what? Caitlin, is this thing polar or non-polar? It is polar. Okay, I can read your lips kind of. But sometimes not. So so it is polar, right? It is polar because they don't cancel. It's not symmetric. Okay. Okay, Caitlin, what are the intermolecular forces then for ammonia? And you'll have to unmute your mic. Just hit the space bar.
Give me 1 second.
Will it display London forces?
Yes. They have London forces, dipole, and hydrogen bonding.
Yeah, okay, dipole, because it's polar. And why hydrogen bonding?
Because it has a nitrogen and then a free electron pair.
Exactly, right? You're missing one thing, though. You're missing one really important thing. So you have the electronegative nitrogen, oxygen, or fluorine. It has a lone pair. What are you missing? There's one more criteria for hydrogen bonding.
I'm not sure, I'm sorry.
Okay, listen to the name of it. Hydrogen bonding.
Oh, it has a hydrogen bond.
Directly to the electronegative nitrogen, oxygen, or fluorine. That's really important, okay? It's got to be bound to the electronegative nitrogen, oxygen, or fluorine. So you're absolutely right. And then, Caitlin, what would be the dominant of these forces?
The hydrogen bonding.
Yeah, again, it's a very small molecule, so the London forces are going to be relatively weak. So it's going to be the hydrogen bonding that's important here. And then finally, we have this guy here. Okay, now again, I know that these guys aren't going to contribute to the polarity. And then we have this carbon here, which again will have 4 bonds. 1 will be to that carbon, 2 will be to the other hydrogen. So the other one must be to that oxygen. And actually, this is just an alcohol again, right? So we've already seen this. This just looks like this. Okay. So, Kaylee, is this molecule polar or non-polar? Push your space bar.
I think it's, well,
Are there any polar bonds in this molecule? Are there any polar bonds over here?
no.
No, right? Carbon, hydrogen, carbon, carbon, non-polar. What about
Yes.
carbon, oxygen?
Carbon oxygen is polar.
Okay. And which way is the arrow going to point? Which way is the dipole going to point?
Towards the oxygen.
Towards the more electronegative oxygen, right? 'Cause
Yeah.
that's less electronegative. What about the oxygen, hydrogen? Is it polar?
Would it go towards the oxygen still?
Yeah, right? Because again,
Yeah.
the oxygen's going to be more, the hydrogen's way, whoops, it is way over here.
Yeah.
So it's definitely less electronegative, right? By a lot. Okay, that's why the hydrogen bonding works. So is this molecule polar then?
Yes.
Yeah, right. If the dipole moments were pointing, they were the same size. I can't get it all in there, but if they were the same size and they were pointing directly at one another, they would cancel, right? But they're not. They're like this. They're bent. So they're not canceling, right? We can see that. They're not canceling. And so there would be a net dipole moment. Again, I don't need you to draw that. I just need you to understand that they did not cancel in this molecule. Therefore, is it polar or non-polar?
Polar.
It is polar. So what intermolecular forces will it display?
London forces.
Okay,
Dipole, dipole.
because it's polar.
And then it would be, would it also be hydrogen bonding because of the oxygen with the hydrogen directly?
One more thing
And then the lone pairs?
on the electronegative oxygen.
Yes.
Absolutely. Okay. 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 Kayla, we need to put ammonia into here somewhere. Where's the ammonia going to go? This is tough. Could you tell me on which side? Am I going to put it on the weak side or the strong side? Or is it going to go in the middle?
Would it go more towards the right side?
Okay, to the stronger side? Okay, so am I going to put it to the right or left of methanol? This could be, of this type of question, this would be the hardest one I could put on the exam. And as you guys are going to realize, I'm not going to try to kill you on an exam. If you're actually doing your homework and you understand your homework, you're going to understand the exam problems are pretty much middle of the road. So what do you think? Am I going to put ammonia to the left or right of methanol?
The right.
Okay, why to the right? I'll tell you, you're correct.
Is it
I want to
because
know.
of hydrogen bonding forces?
But they all both have that. They both have London, they both have dipole, and they both have hydrogen bonding.
Oh yeah.
So why is this one actually to the right of this one? Anybody want to help her out?
Is
Uh,
it because of size?
Say again?
Is it because of size?
Not really.
Is it the lack of the carbon chain on it?
Exactly right. Remember, this part of the molecule is non-polar. So that means I got to break some of my water, right, which has these strong hydrogen bonds. I have to replace some of those really strong bonds and replace them with weak London forces. There's no reason for that to happen. They're not going to release one another to allow us a weaker bond in there. So that's why ammonia is going to be slightly higher in solubility than ethanol, or I'm sorry, methanol. Okay. Then we have ethanol. Is it Eugenie? How do you pronounce your name?
It's Eugenie.
Eugenie?
Yeah.
Okay. Okay, Eugenie, where am I going to put ethanol in all of this? It displays London forces, dipole, and hydrogen bonding again.
Would it go before the CH3OH?
Absolutely, right? It's going to go here. So this is going to be the CH3CH2OH, and sorry about this being a complete mess. Okay. And can you explain to me why you did that?
Because of the carbon. Carbon
Yeah, it was part of it again, right? Again, this can only have London forces. Well, that non-polar part's even bigger than this non-polar part. So that means I'd have to break even more strong hydrogen-hydrogen bonding within the water and replace it with weak London forces, even more so than the methanol. So yeah, absolutely. It's going to be a little bit less soluble than the methanol. Okay. Okay, any questions about any of this good stuff?